Hello everyone, welcome to today's QST seminar. Today we are very happy to have Vasudev Shyam from Stanford University, and he's going to tell us about entropy of de Sitter 3 horizon from finite radius holography. Over to you, Vasu.
Thank you, Abhijit, and thank you very much for the invitation to speak to you all. I'm very keen to visit TIFR whenever the opportunity arises, but for now this will do. So as Abhijit said, I'll talk today about computing the entropy of the cosmic horizon in three-dimensional de Sitter space from holography. But this will be a version of de Sitter holography that most people might not be familiar with, and it relies crucially on the ingredient of solvable irrelevant deformation, such as the TTbar deformation. And I will explain how all of this comes together in a moment. But first, the aim is to provide a calculation of the Gibbons-Hawking entropy as a count of microstates. And for reasons that I will explain soon, I will aim to compute this entropy as a microcanonical entropy of a quantum theory that inhabits the de Sitter horizon. So here, the picture is that the dual theory lives on a time-like surface of some radius in de Sitter space, so a world tube surrounding an observer in their static patch. And the radius of this world tube is set by the deformation parameter in the dual theory. In pictures, what I mean is the following. So each one of these orange curves with increasing color gradient is the locus on which the dual theory lives. And as the deformation parameter is tuned, this surface grows until it reaches an extreme value, in which case it's the stretched horizon. So it hugs the cosmic horizon. In Lorentzian signature, the topology of these surfaces is a cylinder. So basically the spatial circle times time. And in Euclidean signature, we identify time periodically, and this is a torus. And so it's conceivable at this level already that were we to know how to compute the partition function of the dual theory, then we should be able to say something about the entropy. I'll make that more clear, but at the object level, what I'll be computing in the dual theory will be the partition function, as the partition sum over the energy levels. And as you may have heard, if you're familiar at all with the literature on the TTbar deformation and its relatives, we do know very well how to compute the energy spectrum on the cylinder or the torus. So I'll proceed. Now, the de Sitter entropy can be seen in two ways, at least. There's more than two ways to think about it. But for the purpose of my discussion, it's the entanglement entropy of half the central slice at the neck of de Sitter. So if I prepare a quantum state at the constant time surface t equals 0 surface of de Sitter space, and were I to trace out half of it, the entropy associated with that is the entropy of the de Sitter horizon. And this, like any other entropy, can be written, or the reduced density matrix, like in any other entropy calculation, can be written as the trace of e power minus beta times the modular Hamiltonian. And the interesting thing here is that the modular Hamiltonian associated with this entropy is nothing but the Hamiltonian that generates time evolution within the static patch. And so the partition function that I'll be computing is exactly this quantity. So the thermal entropy associated with this partition function computes the entanglement entropy associated with tracing out half the central slice.
Sorry, Vasu, just a quick question.
Yeah.
So here you mean the entanglement entropy of some quantum system that's dual to de Sitter space, or are you referring to like the bulk entanglement entropy?
Here I'm referring to the bulk entanglement entropy, literally of this
Okay.
central, central
Okay.
slice. And this is exactly how in quantum field theory on de Sitter space you would think and compute this entropy. You would essentially try to trace out everything outside the horizon.
Right.
So in many ways it is.
But then you would get sort of this Gibbons-Hawking contribution from the horizon, and that you would have to interpret in terms of some other quantum system. Presumably.
Exactly. Yeah. That's the idea.
Got it. Thank you.
Basu, so you are considering just some quantum field in de Sitter, right?
No, that's not what I'm doing. My claim is that I really will be computing the Gibbons-Hawking entropy, which is nominally a gravitational entropy from a dual theory.
Okay.
So yeah, and as I described, this dual theory will live on one of these constant radius surfaces that I'll push out to the horizon.
Okay.
So thank you for those questions. So this is just the outline of where the calculation will go. Now, one thing to note about de Sitter space is that its geometry it makes it a little bit different from a black hole spacetime when we think about computing entropy there. In particular, there really is just the one temperature. But there is the other fact that Euclidean de Sitter space in all is this four sphere, but we're fibering over it some tori when we look at these constant radius slices, as is easily seen in this parametrization of the metric. So if we take slices of constant radius, then we have the torus formed by the spatial circle and the time circle that's periodically identified. And the M-blackening factor here sets the radius of the non-contractible cycle of this torus. What happens when you actually approach the horizon is that the non-contractible cycle pinches and the torus really degenerates to a hemisphere or a disk. This really happens in any number of dimensions. But for our purposes, what that means is that approaching the horizon takes the high temperature limit for you. So not only will we need to compute the partition function of this dual theory, but we're going to be computing this partition function in the high temperature limit, making it such that what we really need to find is the sort of density of states, the prefactor to 1, essentially, because we're going to be in the high temperature limit. And so we're really looking at a microcanonical entropy calculation here and not a canonical one. So that is the full set of demands here.
Sorry, Vasu, one question, just a basic one. So this slice at half, time, what kind of topology does it have? Is it a sphere?
Yeah, that one is a sphere. Yeah.
And
so basically, the half is going to be a hemisphere. In total, it's going to be a sphere, right? The neck is a 2-sphere within the 3-sphere that would be Euclidean ds. It's like the equatorial slice. And so normally what you would do is you try to cut the sphere in half. Like if I was looking at quantum field theory on de Sitter space, I would try to prepare a state on the sphere, cut it in half, and look at the state on the half sphere. And now the question is, how are you going to get to the half sphere from what look like tori? And so the answer there, and this is something that I picked up from reading this paper of Sunita Varadarajan's from 2002. I bet other people also knew this, but the idea is that this torus has a non-contractible cycle that depends on the M-blackening factor. So as you approach the horizon, this starts to pinch. And when it pinches completely, you're left with this disk. So there's actually a kind of topology change going on there.
Sorry, Vasu, very sorry. I'm a little, I don't know why I'm disoriented by your coordinate system here. Sorry, just help me out. In the standard static coordinate system, wouldn't it be more like something like 1 minus r squared in suitable units dt squared plus dr squared over 1 minus r squared. Your embarrassment factors seem to be going the opposite way.
Well, that might very well be a typo.
Okay.
Apologies for that.
Because I mean, what's your temperature direction? Isn't it E?
You're right. No, it should be the other way around. I'm sorry,
okay.
because
Thank you.
Yeah.
That was really confusing me. Okay, so
sorry.
Right. Okay, thank you. And now your contractible cycle is TE and the non-contractible is phi. Is that right?
Yeah, exactly.
Okay, okay, thank you. And now say again, because I was so sorry. Say again the last thing about the fibering and everything. Yeah, once more.
Sure. Sorry. Oh yeah, okay. So everybody, please make the mental replacement. Thank you very much for the comment, and I apologize for the typo, but please make the mental replacement of the dr squared and the dte squared terms in this line element. And notice that as r approaches L, the prefactor of the te squared term will go to 0, and basically that sets the period of the time circle in this torus. And this is how the torus pinches to the hemisphere that one would normally consider when looking at the Euclidean de Sitter horizon.
Right. Okay.
Yeah, sorry about that.
No, that's fine. Okay. Yeah, go ahead. Thank you. I think I understand what's going on.
Sorry, could I ask what's probably a stupid question? Lorentzian de Sitter space is an S2 times time, right? Topologically.
Yeah, right.
Now, this intersection of this red line with the past horizontal line, should I think of that as living at a particular point, let's say the South Pole or North Pole on S2?
So you mean where the diagonal line ends at the bottom?
Yes.
Yes. So that basically the horizon ends at a point on the asymptotic boundary.
So I could think of this line as coming as a light ray sent out by an observer from the North Pole at t equals minus infinity.
It's really should I? Yeah. That.
So the red line itself would be a circle, actually.
Yeah.
So just an expanding light front.
Exactly. Yeah.
And the other 45-degree red line would be a contracting light front that would converge to the North Pole at t equals plus infinity. Is this right? And these two light fronts would meet at the equator. They would have covered half the sphere at your middle point, half the middle point. Is that right?
Yes.
Okay. Thank you. Yes. And sorry, and then just to understand the topology of one of these curvy red lines.
Yeah.
Are they sort of? Is it that if I'm at some point on a curvy red line that's not the corner points, then it's an S1.
Yeah.
But at the corner points, these S1s have shrunk to nothing.
Yes, I think that is correct. Let me think. So basically, these are all world tubes, which in the limit go from time-like to null. So the red one is really the stretched horizon, and that is, as you said, the penultimate one, where I'm really sending out a light ray. The world tubes are basically, you can think of some congruence of time-like, some massive particle, some congruence
that
of
you're sending, not at the speed of light, but
exactly. Yeah. So that's what they're.
Okay, thank you.
Thank you for that comment too. Great. So I'll proceed from here and go to the field theory side of the calculation. So just to be clear, where the holographically dual theory sits is on one of these world tubes.
I'm sorry, just one quick follow-up. What's confusing me is that that you're talking about these tori.
Right.
The spatial cycle, the time cycle becomes a circle, But if the spatial cycle is sort of shrinking at the ends of the circle, that looks more like an S2 to me.
I see what you're saying. Right. Right. Let me think about that. Yeah, I guess one has to be careful about what it means to really identify asymptotic boundaries.
Yes.
And that's where the question of whether these spatial circles are shrinking or not comes in. Let me just plant a flag there, put that caveat and proceed, because
yes,
alternatively, it's all right. I mean, alternatively, we could just say that we started with Euclidean de Sitter space and we look at a particular coordinate system, or sorry, a particular fibering of tori on that. So we basically look at S4 as coming from a union of two of these collection of torus fibrations over the line, where at the extreme point they degenerate into hemispheres and then we join them there. So we could take that to be the setup from the very beginning. And we could see the Lorentzian situation as coming from sort of the different degeneration of the Euclidean the Euclidean setting. So with that caveat, and just to reiterate, the idea is that the dual theory sits on one of these world tubes and is dual to all the gravitational physics happening within it. And eventually my interest will be in the largest of such world tubes, which will be the horizon. Before I get to what exactly that dual theory will be, I'll introduce the TTbar deformation briefly. So its origins go back to Smirnov and Zamolodchikov and this paper by Cavalia and collaborators. What it is solvable deformation of quantum field theories in 2 dimensions by a certain composite operator constructed from the stress tensor. Covariantly, what TTbar is this contraction, this particular contraction of 2 stress tensors at coincident points. Why it's called TTbar is when you go to complex coordinates and you're deforming a conformal field theory where the trace is 0, this combination just becomes T times T bar. But what you should think of when I write this down, this abusive notation, is the expression on the right-hand side here. What makes this deformation solvable, and by solvable, I mean certain observables in the undeformed theory can be followed along the trajectory that the deformation triggers, is this factorization property of the composite operator in question on spaces that have translation invariance, in particular the plane or the cylinder. And the idea, roughly, is to infer a flow equation for the energies from this kind of equation for the partition function or the action. We write stress tensor components in terms of the energy and the pressure and the momentum. And then on the left-hand side, we have a derivative with respect to the deformation parameter of the energy itself. And we infer that the energy must have a certain flow equation. And in that way, we understand how the energy levels are deformed level by level. I'll explain this a bit more slowly. Yes. So basically, in equations, what I just described looks like this. The mu derivative of any given energy is proportional to the expectation value of the TTbar operator in one of the energy eigenstates, and these translation invariant eigenstates. And using this factorization property and using my knowledge of the various stress tensor components as either energy, pressure, that is the R derivative of the energy, or momentum, I can expand the right-hand side in terms of all those quantities. And I infer the following nonlinear first-order equation for the flow of the energy levels, which has the form of Berger's equation from hydrodynamics without viscosity. So inviscid Berger's equation. If we started with a conformal field theory, then the solution to this equation is what I've written down here. And for future reference, I will denote by E0n this combination of conformal weights and the central charge, which are the energies of the various CFT states on the cylinder, and the angular momenta are the difference. So everything that is to follow, I just want to make this impression now. So everything that is to follow comes from just this observation about the spectrum. Anything we can say about the torus partition function really just follows from, taking this equation for the energy levels, recalling that Z is trace e power minus beta h, and then working out what should happen to the partition function. So all this calculation of the entropy we'll know about is properties of the spectrum. So
Vasu, do you want the 1 over R in Jn?
That's a good question. I think I do in this convention. I will look at RGN, which is just a difference later. So yeah. I don't know if that's what people normally call momentum, but for now I'll keep it, and later I will get rid of it. By later I mean now, literally, because I want to write everything in terms of dimensionless quantities. And when I'm deforming a CFT, because the only scale that's introduced is that's associated to the TTbar deformation, I can measure it in units of the radius of the cylinder. And so this deformed energy is just a function of the ratio of the deformation parameter to R squared, which I will call lambda.
So very, very sorry, Vasu, to interrupt.
Sure.
Excuse me. But just before you go on, can you go back 2 slides to that picture with the trajectories, just to, one more, please, which is, so as you vary mu, the scale, are you in a sense choosing different foliations? Is that the way I should think about it?
No, I'm moving along the foliation. So basically, mu sets the size of the world tube.
I mean, foliation meaning, are you moving along the world line of a Rindler or whatever observer, or are you going to?
No, I'm choosing a different world tube.
Yeah, that's what I thought.
Exactly.
So you're choosing a different world tube and going out towards going towards the horizon would be going towards lower mu. Is that right?
Higher. Yeah. So it'll be easier to see. Well, actually,
if you can come to it, that's fine. I just wanted to try to map.
Right. Yeah. I think you're right that it'll be lower mu. Well, no, sorry. It is higher mu. Basically, the maximum value of mu is the one corresponding to the horizon itself.
I see. Okay. So Okay. Go ahead. Thank you.
Thank you for the question, though. So the quantity that I will use actually will be this lambda, which is a dimensionless ratio of mu and R squared. And I can write the Berger's equation purely in terms of this lambda, which will be very useful to us in what's to follow. And curly E sub n is R times En, which is once again dimensionless. And this quantity is purely a function of lambda. All of this is just rewriting of the formula we already knew in hindsight of knowing the solution over here. As you can see, mu always appears in this ratio, mu over R squared.
And what do you do about the plus minus? I mean, sorry, I'll be commenting on all this later, but just to understand, because if mu is growing bigger at some point, the minus.
Yes.
Okay.
Right. So thank you for that question. So we will choose here the minus sign. And this has a little bit of history because there was the original proposal of Meghoff, Mazet, and Verlinde, where they looked at the pure TTbar deformation and the analogous setup within ADS3. So the idea is that the pure TTbar deformation pulls the asymptotic boundary inwards. And once again, the radius of this boundary is set by, is related to mu. And there you choose the negative sign, and people call this the holographic sign. But there's a caveat here, because the negative sign in the setup that we're considering here is a sign where we look at filling in the inside of these world tubes. If I were to flip the sign, I would do the opposite. I would basically, from the Euclidean path integral point of view, I would fill in the outside from the horizon inwards. And that is related to some work in progress currently that Ronak Soni, Evan Coleman, and Sang-Jin Yang are working on. But yeah, there is some holographic meaning to both of these signs. For now, I'll stick to the negative sign of mu. So thank you for that question. And corresponding to this negative sign is growing the world tube, and I am looking at gravitational physics within the world tube that's being that is dual to observables that are defined on the world tube, so to speak. Yeah.
So sorry, Vasu, my understanding was that for De Sitter for one to interpret De Sitter in this TTbar language, you also have to introduce this lambda deformation.
Sure. I'm getting to that.
Okay. So your comments so far were about ADS. Is that right?
Yeah. So far we're still talking about ADS, and this is basically the picture that I just explained. So in the bulk, how we view this TTbar flow, pure TTbar flow, is in this truncated ADS space. And so as I increase the deformation parameter, I'm actually moving in to ADS3. And now what we want to do is get to the De Sitter space. And this is what Onkar was alluding to. We have to include, in addition to the TTbar deformation, the boundary cosmological constant as measured by the TTbar coupling, or as measured by the deformation parameter, which is what this 1/2 lambda squared term here denotes. So this is what Gorbenko, Silverstein, and Toroba called the lambda 2 deformation. So in total, you have what's called the TTbar plus lambda 2 deformation, which again defines an irrelevant deformation, which is solvable of conformal field theories in particular, but other field theories in general. However, because I'm deforming by something that goes like 1/lambda, I need to have done the TTbar deformation first. So you see, if I had started with that, all I would be doing is adding a trivial term to the effective action of the CFT, something proportional to just the cosmological constant. And that's just a local counter term. We don't really care about it. However, what we call trivial in a CFT is based on word identities that usually take the form, trace of t equals various things, or trace of t inserted in correlation functions equals various things on the right-hand side. And the highest power of the stress tensor appearing in the word identity is the first power. So that's why if I just add, the cosmological constant term, then I can just trivially shift the stress tensor, and it's just a simple counter term. I can get rid of it. When I have the TTbar deformation, the word identity involves something quadratic in the stress tensor. So what I would call trivial might not be anymore. And that's what makes this addition of the lambda 2 deformation after doing the TTbar deformation non-trivial, because the rules are different now.
Sorry, just to understand that,
sure.
All that shifting the cosmological constant does in any field theory is to shift the ground state energy.
Right.
And now you're saying that if I've shifted the ground state energy, then deforming the theory by TTbar is different because T includes the ground state energy shift, right?
Exactly. Yes. Yes.
Thanks.
Thank you. Now what we have is a situation where we either turn on this cosmological constant or not. And it's convenient to consider the superset of both of these deformations in terms of this general equation. I've introduced this parameter eta. So if eta is 1, then there's no additional term, and it's the original TTbar deformation. If eta is -1, then I do have this additional term, and that's the TTbar plus lambda 2 deformation. Why I include it is because the boundary conditions for the differential equation that I've written above aren't set at lambda equals 0, because naively that would just diverge. Instead, they're set where I can compare them with the pure TTbar deformation. So basically at very large lambda. There are other choices one can make, and this too is a topic of ongoing interest in research. But for now, I'll keep this general equation and proceed to find the flow equation for the partition function that follows from this general equation for the flow of energy levels. So as I mentioned before, we can infer the flow equation for the partition function from knowing the flow equation for the energy levels. This isn't how the authors of the papers, so Shubik Datta, Yunfeng Jiang, and collaborators, this isn't how they originally found this flow equation, but what Martinek, Sethi, and others noted in a paper where they were trying to define TTbar on ADS2 was that you can just take the flow equation for the energy levels, note that Z is a partition sum, and then work out the equation that Z has to satisfy by doing some integration by parts, essentially. And from that procedure, you'll land uniquely on the following second order differential equation for the partition function as a function of lambda, the deformation parameter, and the torus modulus. So the real part I denote tau1, and the imaginary part I denote tau2. The imaginary part of the torus modulus is the dimensionless temperature, and the real part sets the periodicity of the spatial circle. And here too, the 1 minus eta factor carries over from the equation that we had before. So this is still the superset of both the TTbar and the TTbar plus lambda 2 deformation. And the energy levels now, the modification that the eta leads to is this modification within the square root. I've already committed to the negative sign for mu, as was discussed earlier in the formula that I present here. So everything that's to follow will rely on this equation, which was a direct consequence of the equation for the flow equation for the energies. Just so we
Sorry, I forgot what eta was, please.
Yes. So eta is just a bookkeeping device. Sorry, the slides are not cooperating. Yeah, eta is just a bookkeeping device that lets me know whether I'm turning on pure TTbar or if I'm adding lambda 2. So if eta is 1, then I have just the TTbar deformation because the term in the bottom equation, the last term on the left-hand side is 0. If eta is -1, then it's what I get from the TTbar deformation.
Thank you.
No problem. Sorry about
Vasu, just show that last slide you were showing with the. Yeah, sorry. Just to ask you, I mean, so you're going to work with eta equal to -1. Is that correct?
Correct.
And then is it that because of the lambda square term, somehow the way the energies and jns work out, the square root is still always positive? Or,
no.
Or what?
So that's a good question. The square root is not always positive, and that's an important part of the story. So when I said that there's an extreme value of lambda, there's the largest value of lambda, which corresponds to this time-like surface hugging the horizon, basically it's the value of lambda where the square root vanishes.
Okay.
And so and beyond that, there's seemingly complex energy levels. In the ADS case, the bulk interpretation for what's happening with the analogous expression when we have these levels, these square imaginary levels, is that the cutoff surface is encroaching into the black hole. So basically, at the cutoff surface, at the cutoff value when the square root vanishes, the surface sits on the BTZ horizon. Beyond that, it's as though you've entered the BTZ black hole. And honestly, you can't really call this an energy anymore, because from the bulk perspective, light cones have flipped, and now this isn't really a time-like direction. So there it makes some sense, at least from the holographic perspective, that these energy levels don't remain real. In the de Sitter case,
sorry, Vasu, can
sure.
I just, I'm still confused about the signs, because
right.
If I'm outside of the de Sitter horizon, lambda takes a smaller value, and then I get to the de Sitter and lambda takes its maximum value, right?
Yes.
Now,
yes.
the lambda square term, Jn square term, actually helps with the sign of the quantity under the square root. So, isn't it the other way around, that for smaller values of lambda, you have more, you're -1, okay, sorry, go ahead.
Sure. So note that the ground state energy is negative. And
that's
so
the Casimir.
Yeah. So it's the minus C/12. And then eta for the de Sitter case is -1. And for now, I'll just look at states that have zero angular momentum. In particular, if I'm looking at empty de Sitter space, and I'm just looking at the cosmic horizon of empty de Sitter space, and I have zero angular momentum, then it becomes a bit more clear what's going on. I have -1 plus 4 pi lambda times C/12.
Okay, I see.
So you see, this is where
the ground state, and then as you go to higher and higher excited states, this will flip over at some point.
Yeah. So there's a set of states corresponding to point particles in de Sitter space, which are kind of safe.
Okay.
Yeah.
Okay. Got it. Okay.
Yeah. Well, thank you for the question, though. That
no, but and I'm sorry to interrupt so much. You must go on. And then you have some interpretation for the other states where the square root turns over.
Not yet. We wish we did, but there's a sense in which they will implicitly contribute, because I will be computing the density of states eventually,
okay.
And the density states that I'm computing just comes from taking the entire partition function in the sort of large C limit, and the theory that I'm deforming has a gap in a sparse spectrum. But nevertheless, when you do the usual moves like I would in a CFT, using modular invariance and so forth, I am summing over all of these other seemingly complex states to get the vacuum in the cross channel. So there is they seem to be important. If the calculation that I will present, this Euclidean calculation, isn't just some gadget like it sometimes ends up being, but it really is a microstate count, then there is some meaning to these other states insofar as they contribute to the behavior of the high temperature behavior of the partition function, essentially.
Basu, what you were saying, does it mean that the partition function that you have written will be modular invariant at the end of the day?
Yeah, so I want this to be modular invariant, and for it to be modular invariant, as Datta and Jiang noted, lambda has to transform as a -1, -1.
Right. And then what does it cut off mean? Because isn't that cutoff means that you are,
yeah, I'm not cutting off. That's basically what I'm saying.
Okay.
So I'm going to tolerate seemingly complex partition function, but with the bonus that I will have modular invariance. And as we will see, the density of states and the entropy is still real, and they seem to give the right answer. And by right, I mean the one that captures the right bulk physics. So thank you for these questions. So the link now to the bulk is, in a sense, very simple. all we need to do is change variables from lambda, which is this -1 -1 modular form, to V, the volume of the torus. And as I mentioned before, I'm measuring the deformation parameter in units of the radius of the cylinder or the torus. And I can do this the other way around, which means the volume is related to the ratio mu over lambda. And again, my partition function and energy levels are all functions of V, or it can be rewritten as functions of V, just as well as they were functions of lambda. I define this quantity psi that I have suggestively named, which is the phase e power minus V over 2 pi squared mu times the partition function, now seen as a function of V and the moduli. And I notice that the equation that it satisfies is the radial Wheeler-DeWitt equation that I would get from quantizing gravity in 2+1 dimensions in the constant mean curvature gauge. So a bit more slowly, what I do is take Euclidean gravity, fix slices of constant mean curvature, and in 2+1 dimensions, doing this leads to essentially a finite dimensional phase space, which is to be expected because a complementary way to think about gravity in 2+1 dimensions is in terms of Stern-Simons theory. So you would expect that there should be some simplification occurring in the canonical picture too, in the metric picture too. And the way, at least in the literature, that people manage to see it is by fixing slices of constant mean curvature, and then just quantizing the system that sits on this finite dimensional phase space as you would a mechanical system, just to get this simple Schrodinger-like equation, now written in terms of V and the derivatives with respect to the modulus. And again, here eta appears, and as you'll see, eta sets the sign of the cosmological constant, which is what we want. So again, there's another sign flip. So if eta is 1, then we have a negative cosmological constant. If eta is -1, we have a positive cosmological constant, and we're in de Sitter space. I've written now these bulk constants, like Newton's constant and the cosmological radius. They're related to mu in the following way. So 2 over pi times the product of GL is mu. So mu has dimension of length squared. And C, like what we are familiar with from Brown-Henno, is the ratio. It's 3/2 of L over G. So the ratio is C and the product is related to mu. And this is a very simple translation. So the bulk interpretation is just coming from using different, it's just manifest by looking at a different set of variables for writing this equation down. So here's our bridge. Next question is, what is the semi-classical limit? So in terms of the quantities on the boundary, what we want to do is keep the product of lambda c fixed. So I'll call that lambda prime. I've added a factor of 1/3 for convenience later. So I keep L squared over R squared fixed while taking C to infinity and mu to 0 simultaneously. And that is the same as taking the semi-classical limit in terms of the bulk psi. So it's like the WKB limit of this wave function. And what I find is, from knowing the form of the deformed energy levels, I can easily infer the form of the action on shell, or Hamilton's principal functional, which is the exponent in the WKB wave function. And it takes the following form. Note that here, in order to survive this limit, I need the weights in E0 and J to scale with C. So that also fits our intuition that we need some heavy states that contribute in the semi-classical limit. And also, instead of having a partition sum, I'm now localizing onto one level. So this is how this formalism digests what we normally expect from holography. And the square root is exactly the one that you would have in the energy formula. And this brings us back to Professor Trivedi's question about what happens when we hit the zero of the square root. So the square root has a single, so again, we'll focus on states with zero angular momentum. And eta has two signs corresponding to the ADS and DS case. When we have eta equals 1, so when we're in ADS, when we hit the singularity, we have the BTZ horizon with curly E naught going like 8 GM times L, which is what we would normally see for spinless BTZ black holes. When eta equals -1, we have the flipped sign. And for this flipped sign, the simplest state that sees this singularity is the ground state. And the ground state in my units is the one where lambda prime is 1. And we can also have certain point particle states. So in de Sitter, you don't really, in DS3, you don't really, it's not that simple to fit black holes, but you can have these conical deficit states, which are like point particles. And I will focus not on those, but on the vacuum. So this is how we see the cosmic horizon from the formalism that we have here. Once again, we'll go back to the picture that I had before with the typo that I had before, unfortunately. And now we see that what we want from the boundary theory is the partition function on this torus with the very small time circle at lambda prime equals 1. So at this extreme value of lambda. And we want to do the inverse Laplace transform to compute its density of states, from which we get the entropy. So yeah.
I'm sorry.
Sorry.
Whoever.
Okay, Shiraz, go ahead.
Yeah. Sorry, lambda was that the coefficient behind TTbar?
It was the coefficient behind TTbar and also the coefficient that sets the cosmological constant. So
okay.
In some sense it was both. Yes.
And you said your lambda scaled like 1/c. Did I get that right?
No. So let's see. Lambda prime is this combination of lambda c that I'm holding fixed.
And
lambda,
therefore lambda scales like 1/c?
Yeah.
Okay, so it's a little like large n scaling. So each t is like a single trace operator.
Exactly. Yeah.
And you're dividing by n. Okay. Fine. I had a more general question, but after Sandeep. Please
okay.
Go.
No, okay, thanks. No, actually, can you just go back? I'm confused about something really simple. I somehow feel I should call you Professor Vasu, but if we mutually agree not to, then I won't. Okay, Vasu, question, which is, are you looking at just pure gravity in ADS3 and you are going to try and explain the entropy of the de Sitter horizon in that theory? Is that what you're trying to do through a TTbar deformation? Or what exactly is are we trying to accomplish here? Sorry. Again,
right. So what I'm doing is computing the density of states of this TTbar plus lambda 2 deformed CFT in a certain scaling limit. Right?
Okay.
The bulk interpretation of this scaling limit is what I would get from looking at the semi-classical limit of the quantization of pure 2+1 gravity in constant mean curvature gauge.
I see.
Now, so whether that means that the entropy calculation only needs the gravitational sector or whether it needs more is something that I will remain agnostic to, because it'll all rely on whether the results of this calculation can be seen as an honest count of microstates or not. But as we know from the black hole case, you can have your cake and eat it too. Like you can just have a semi-classical gravity calculation that seems to know something about, like you can compute the trace over the microstates, even if you don't know what the microstates themselves are. So for now, that's what I'm doing. Yeah.
Thank you. Sorry. Shiraz, go ahead. Sorry.
Yeah. So are all your computations going to be done in Euclidean space?
Yes. Yes.
So then I just wanted to understand these slices. Could you help me a little bit? Is Euclidean a three-sphere?
Yeah. Yeah.
Okay. And then what are these? Can you tell me what these curvy red lines are in Euclidean de Sitter?
They're tori, which is a weird thing to say. So
I see. So
it's a kind of torus vibration of the line, which has some. So basically, you can think of it as a union of two torus vibrations over like half line, where at the ends the torus degenerates to a disk.
So can I think of it this way? So if I think of an S3 embedded in R4 or embedded in C2, then I've got I've got an angular rotation in each of the C's. Yeah. And these are my circle directions. Correct. Is this correct? Are these the two circles that you're getting? The two circles are rotations in the first C and the second C.
Let me tentatively say yes. I would have to think about this a little bit more carefully, but tentatively yes. Okay.
And then you say these tori degenerate at special points.
Yeah.
Okay, fine. Thank you. Okay. Yeah. And one last.
Sure.
Yeah. Well, you talk about this quantization. So the state is going to live on this torus. That's going to be like space for your quantization.
Yeah. Exactly. It's sort of radial.
Right.
Quantization, not to be confused with the other kind of radial.
So I shouldn't really think of it as the state of the Lorentzian de Sitter space, right?
No.
It's an auxiliary.
Exactly. Yeah. So how to think about it is a good question. So Onkar has some work about relating this kind of radial quantization. Well, not just Onkar, but in the context of the TTbar deformation. What you naively have access to is this radial slice, but you can also work your way towards the state honestly on the time slice. And so they're not entirely unrelated quantities because of diffeomorphism invariance, but they're not. It isn't something direct either. Yeah. So thank you for that. My reason for looking at these radial slices is because what they do limit to, these surfaces, is the horizon, right? The stretched horizon. And you can think about an honest quantum state on the horizon if you wanted to. So that's sort of the reason here.
Sorry, Vasu, just a quick question.
Sure.
So my understanding of this DS story was that it's sort of a two-part flow where you flow from the UV CFT to the IR of ADS, and then you sort of flow out. But from what you said here, it didn't seem like you had a two-part flow going on. But so am I just being confused, or?
I just showed you the end result of doing something like that. As in, I just showed you this action, these energy levels. That solve the flow equation that I put forward, but I didn't tell you how, right? So if I really wanted to do that, what I would do is look at the large lambda limit, which is basically the limit where where these things are really small, right? Like these tubes, and then I would compare that with ADS, and then I would I would match it there. But you don't have to do that. You could do it at another point, and this is something that we've been discussing with Eva and others, is to sort of understand.
I mean, just from the de Sitter perspective, like I don't have anything to compare with if I sort of go out to larger and larger values of capital R, right?
Not quite. Well, okay. So we should be careful there, because one thing that we will notice is that the Gibbons-Hawking entropy comes from, the Gibbons-Hawking entropy really looks like the BTZ entropy computed from the Cardy formula with the C/6 level, right? So near the horizon, these two configurations don't look that different. So if you really wanted to,
right. Sorry, what I meant was that if I, in de Sitter space, if I go to like your one, like the North Pole or the South Pole of the hemisphere, which I think maybe is are going to smaller and smaller ones. So there I don't have anything to compare with. But in order to like compare with some quantum system, I suppose I have to like go to large or R close to the horizon and then compare with the ADS.
Yeah, well, you could do two extreme things. You could either go very close to the horizon, or you actually could go, like you take very large mu instead of very small r.
Sure.
And then you can compare with what you get by doing a lot of the TTbar deformation.
Right.
And this is Victor and Eva's and Gonzalo's original idea.
Okay, but that's the basic idea is the same as DS.
Exactly.
Yeah. Okay, great, thank you.
No worries. So now we get to the density of states, which is given by this inverse Laplace transform. Pardon the bizarre notation, that's just to keep consistency with what's in my paper. And basically this frac E is 2 pi times curly E. But other than that, it's just the inverse Laplace transform that one is accustomed to when computing the density of states. What I'll actually do, though, is instead of trying to compute this in the saddle point approximation, which is one way to get the entropy, I will work out a flow equation that the entropy, that is a log of this density of states, should satisfy, knowing the flow equation that Z has to satisfy in the semi-classical limit. So I'll restrict my attention to the zero angular momentum states, where frac E is frac E bar, they're equal. Then the flow equation for log Z implies the following equation for the entropy. And by method of characteristics, I find that it has to be, the entropy has to be a function S naught of the following combination of E and lambda. Well, I'll first take eta equals 1, the ADS case. This goes back to what Onkar was talking about, that in order to really understand what's going on with the TTbar plus lambda 2 flow, you need to do some TTbar deformation first that sets a boundary condition. So first, let's take the pure TTbar case. And then at lambda equals 0, I know that the theory has to limit to a CFT because I deformed a CFT to begin with. So I take eta equals 1, that is a pure TTbar deformation. And then I take lambda to 0. That gives me the conformal field theory entropy. I know how to compute the entropy of holographic CFT, and that's given by the Cardy formula. And that lets me fix this function, S naught, and I get the following result for the log-corrected entropy of the BTZ horizon with this finite radius cutoff. It would be the horizon if I took lambda to a certain extreme value, but generally it's the entropy that I get for the TTbar deformed theory on one of these finite radius cutoff surfaces. This matches the result that Shuvik Datta and Yunfeng Jiang found by doing the direct inverse Laplace transform. Then what we do is for very large mu, that's very large lambda, we demand that S in the eta equals 1 case matches S in the eta equals -1 case. So basically this is like the very sort of redshifted zone in DS matches the deep interior in ADS. That's the intuition for where we compare the two quantities. And by doing this matching, we get the corresponding eta equals -1 entropy. In other words, all I've done here is said that I need to set boundary conditions for the TTbar plus lambda 2 flow in terms of the TTbar deformed theory, because I can only introduce this lambda 2 meaningfully once I've already done the TTbar deformation for reasons we discussed a few slides ago. Having done that, I fix boundary conditions for the TTbar plus lambda 2 flow to compute the entropy, the microcanonical entropy as a function of energy and lambda, dimensionless energy and lambda. And I get the following result. Then I want to take this to its extreme value. And that will correspond to when E goes like 1 over lambda, which is C pi over 3. And then what I find is the log-corrected Gibbons-Hawking entropy when I use C is 3L over 2G.
Sorry, extreme value is where the square root becomes, where the argument of
The
the
square root
is
is 0. Yeah, exactly. Yeah. In the energy formula, not in this formula. And so this is how I compute the quantity that I was discussing before. That is the high temperature partition function at lambda prime equals 1. And as promised, it computes the Gibbons-Hawking entropy for us with the leading log correction. And so the question now is whether this was so this really is a sort of microstate count that's producing this entropy, or if it's just a mirror of the Euclidean gravity calculation. And the answer to that so far is inconclusive, that's work in progress. But it is promising that we can get this result from a field theory calculation. So with that, I will thank you all for your attention.
Thank you, Vasu, very much for your very nice talk. Let's all clap. Questions?
Sorry, can I ask, if you don't mind, just a minor, sure. I mean, you said it, I think, many times, but, you showed a Wheeler-DeWitt equation.
Yes.
And you said that it was the bulk Wheeler-DeWitt equation.
Yeah.
Also, right? And now after that, when I started thinking, I got confused because where does the TTbar if I just took square root of GR and I went to whatever gauge and I constructed the Wheeler-DeWitt equation from whatever constraint, etc.
Yeah.
Where does the TTbar deformation show up there?
Good question. Yeah. So,
okay.
So the structure of the Wheeler-DeWitt equation normally is something that involves coincident metric variations of the wave function.
True. Very.
Right.
Yeah.
So now let's go to the equation that I wrote down here. Notice that all of these derivatives of tau 1, v, etc., are all derivatives with respect to zero modes of the metric. Right. So what happens in the CMC gauge in 2 + 1 dimensions is that the non-zero modes are all quenched. Due to something called the Lishnerowitz equation, you basically solve for the non-zero modes. And all you're left with is a mechanical system that involves the zero modes. So instead of having my usual KAB minus trace K squared type structure in the constraint equation, I'll have some constants, just some zero modes. And that's where it's coming from. And this coincident metric variations are just the same structure as TTbar. So if I go further back, sorry, I went too far back. Go a bit further. Yeah. You see this contraction structure between the two stress tensors is exactly the one that appears between the momenta conjugate to the metric on the slice in the ADM formalism.
The extrinsical. The metric. Okay. Thank you.
Vasu, I want to ask. So if we look at that paper of Verlinde and Mark Mezai and all, where they first proposed this cutoff ADS picture, they matched the quasi-local energy of the black hole with the spectrum, right?
Correct.
So
yes.
What should I look at in your setup? I mean,
the same thing.
The same thing, right?
You'll still have a quasi, you can compute the quasi-local energy from the Brown-York stress tensor, and for pure DS and for point particle states, you can check that the energy matches from what you get by doing TTbar deformation.
Right.
This TTbar plus 92.
Right. So for a physical black hole, the size of the black hole must be bounded because of this imaginary thing, the energy becoming complex. But in the partition function, it seems like you are allowing all possible energy states.
So that's a good point. So there's a sorry, go on.
No, carry on. I just want to ask where it's where should I look at in the bulk? I mean, how do you interpret this complex states in the bulk?
That's a good question. We don't have the answer to that yet, and it's unclear. So again, what we're doing with the partition function is we're really looking. Sorry, I'll just try to skip forward to the slide. We're really looking at the partition function in a particular scaling limit. And if we look at what it is that we're actually deforming, it's really the large C partition function of Hartmann, Keller, and Stoica that where they basically use the large gap and the sparse spectrum to constrain what the partition function at large C should look like. And to leading order, all you're going to see is the vacuum running in the direct and cross channels, right? So it just knows about the universal data. Everything else is suppressed in 1 over C. And to that extent, all you're really going to have is this square root issue with coming from the ground state, and well, that's it, right? Now the question is, what did you do first? Did you first, you know, do the partition sum in the CFT and do all these deformations, or is there some meaning to doing the deformation first and then looking at what's going on? We don't know the answer to that question yet, but you see, it's conceivable that you can get away, you can skirt around the complex levels because you never had to have flown them in the first place. You could have just used the large C partition function of Hartmann, Keller, and Stoica, and then done the deformation, and you'd find the same result, at least to leading order, and you'd also be able to capture the leading log correction. Yeah, so that's the intermediary answer.
So you are saying that you are saying in some sense that the universal features doesn't care about the complex energy states, or
in the asymptotic, either in the asymptotic limit of very large energy in the Cardy regime, or if you're looking at deforming a holographic theory with a large gap and a sparse spectrum.
Yeah, but this is
this
is what I'm confused about, because you are saying large energies, right? But we know that at large energies there are these issues in the field theory. There are these complex energies.
Right.
What do you mean?
Right. That's a good question. So let's see if I can pull this up. So by large energy, I really mean when I can compute the inverse Laplace transform of this quantity in the saddle point approximation.
And the saddle may be complex.
Saddle may be complex, yeah. So the saddle may be complex, but the result seems to still be the one that agrees with the Cardy formula, basically. So actually, let me go to this slide here. So the middle result, right, for the pure TTbar deformation, this is what Truick and Junfeng derived in one of their papers a while ago. And one thing to note is that this is just the same as the Cardy formula, where you take the undeformed energy and express it in terms of the deformed energy, right? Like you invert the relationship between them. So it's really like you're taking the original, it's like a spectral flow, right? You've just taken the original density of states and you've just sort of tried to push it.
That's because the map is 1-to-1. The first state goes to the first state, the second state goes to the second state.
Exactly. So you will arrive at this result whether or not your energies go complex. This is just what it is. That you'd get from the saddle point analysis.
Okay.
And strictly speaking, in a generic theory, that's only valid at large energies.
So what you were saying, that if I take the positive value of, the value of lambda, that will give me a real spectrum, and analytically continue that lambda, I will match all your equations.
Well, yeah, we have to be careful about that. This is a calculation that some people are trying now. And I won't comment too much more about that, but there is a chance that there is some meaning to that too, which doesn't run through the complex energies.
I see.
You see, in some sense, having complex energies isn't the worst thing from the bulk point of view, because at least in the ADS case, we have some interpretation for what it means to try and go into the interior, right, of the black hole. And if you're in the interior, you're not really matching what looks like energy on the field theory side to what looks like energy in the bulk side, because now that's like a space-like direction. It's no longer time-like, and so you have something else going on, and so you can accommodate what looks like a complex energy. Whereas on the other hand, naively, you just might look at some state, right, might have a nominally positive energy, but you might not know how to interpret that from any configuration in the gravity side, right? There's no guarantee that there's some configuration that has that energy. So details of the microstate count is sort of the important part of the physical question to come next. But for now, it looks like we can at least get the sum right.
Okay.
Yeah.
So you would interpret these complex energies as not a pathology of the theory, but some features that we need to understand.
Yeah. Just because it's, to the extent to which we're modeling bulk physics, right? Okay. And that's what seems to match the bulk physics.
Okay. Yeah. Okay. Thanks. Yeah.
No, thank you for the question.
Vasu, I have a vague question about this calculation. Does this calculation suggest any sort of tensor network interpretation for de Sitter space?
I wish I knew enough to answer that question. I mean, yeah, I'll just leave it at that. Yeah. It would be nice to know. Yeah.
Okay. Thank you.
Sorry, Vasu, there's still something. I'm sorry. Is it really the case that the horizon corresponds to the ultraviolet in the field theory? Or did I misunderstand you? Well, sorry.
Sure.
That's very disorienting for me. I mean, if that's the way it works.
Well, it's harder to talk about ultraviolet or to have good intuitions for what's ultraviolet versus what's infrared, because the large value of lambda, it's what it really corresponds to is the maximal extent of delocalization of local objects in the undeformed theory. So I don't know if you would call that ultraviolet, but yeah, it corresponds to the.
Yeah. Go ahead.
Yeah, so it corresponds to at least I'll talk about the pure TTbar case where there is work to substantiate what I'm saying. So Cardi and others have a picture of what happens to local operators under the TTbar deformation, and the answer seems to be that they gain an extent, they delocalize with the size that's set by the deformation parameter. And
but okay, sorry to interrupt, just to understand it. Sure. I know almost nothing about TTbar deformation. So let's say you turn on the TT deformation and you flow to lower energies. Presumably the size of what had been local operators at the cutoff, the corresponding size of the excitation becomes bigger and bigger. Is that the picture?
Sorry, something is that the picture breaking up a lot.
Just to understand.
Yeah, well.
No. Yeah, go ahead.
So yeah, it's just that you were breaking up a lot, so I didn't get your question. Could you please repeat it?
Oh, okay. I'm really sorry. As you flow to the infrared, I suppose the size becomes bigger and bigger. I mean, that's all I was asking.
Yeah.
That is,
well. The problem is if I'm doing an irrelevant deformation, as I follow the deformation, I'm actually headed along the UV critical surface. So I'm not really flowing to the infrared. I'm flowing away to something else. I mean, the CFT in some sense is to the infrared of the TTbar deformed theory. The RG flow drives the deformation parameter to 0.
Yes, I agree.
So the question is how unfield theory like is the theory when we deform it, and at the horizon it seems to be maximally maximally
unfield.
Yeah, for lack of better words. Yeah.
Okay. That's why you said it's more like the ultraviolet. I mean, it's more where the deformation is very important.
Right, exactly. Yeah.
Sorry, I'll ask a couple of questions that will reveal how poorly I've understood everything, but let me just it seems to me there were 3 parts, at least when I try to put your talk together logically in my head. There's a part that is just about the field theory, which I thought was very clear. That was how the density of states evolves is as a function of energy and the deformation parameter, and you solve that, you've got a beautiful answer for that. Then you had, let's just stick to ADS for a moment.
Yeah.
Okay. Then you had a map relating the deformation parameter to a particular location in space.
Yeah.
I didn't understand that map. I'll ask you about that for a moment. And then finally, once you had that map, you related that the entropy in the field theory at that energy to some quantity at that corresponding place in space.
Yeah.
I think you related it to the entropy of the black hole whose horizon would have lain at that point. Is that right?
Yes. Well, when the surface is a horizon, yes.
When the surface and if it's just some general surface, is there an interpretation to that?
When it's just a general surface, honestly, no, not really.
Okay, fine. So could you tell me about step number 2? How did you get the map between a location in space and the coefficient of your TTbar parameter? Could you say that again? I know you've said it, but could you say it again?
No, that's a good question. So, okay, I mean, I can show it to you in a coordinate-dependent way right here. The lambda is the deformation parameter of the lambda is a sort of dimensionless TTbar deformation parameter, and it goes like 1 over r squared, where r is the radius of the cylinder, but it's the same r that appears in the metric in the dr squared term. So this is one way to see that. But I think that a slightly more invariant way to see it is
what I'm really looking for is just a reminder of the logic. What was the logical step that helped you to relate those two?
Right. So really, it's this change of variables here that relates 1 over lambda to v, the volume. And in the constant mean curvature gauge, you see.
So as you go in, you know what the volume is, and that's the relationship. Okay.
Yeah.
I see. And just one last follow up on this. So now you say in ADS at some point this surface would flow to a horizon.
Yeah.
Are you doing this flow inside of the finite temperature, the geometry?
Yes, you can do it. Yeah. So basically, I have a solid torus, right? The BTZ geometry that I'm slicing by the torus. And at some,
I see. But suppose I just started with the 0 temperature, just empty ADS.
I
did my flow, then I would never get a horizon?
No, you would just, so basically what that corresponds to, sorry, I'm jumping around, but okay, let's look at the square root formula. If eta is 1, and then if I have curly E naught being C minus C over 12, then this is just going to be a well-behaved function. Like the square root will never go to 0, and I just won't see.
I see. So the rule is that I'm supposed to do I'm not understanding. Why can't I do this flow inside pure ADA? If I do this flow,
you can.
I can, but there's no. Then I should not be looking for this S of an interpretation for this S of E.
No. In the bulk, no.
I'm just not understanding logical flows.
Sure. So let me think about how to answer this question. So in the bulk, what that S of E corresponds to is the log of the Legendre transformed wave function. So it's the phase of the Legendre transformed wave function with respect to tau2. Right, so it's like going from position to momentum basis, where position here is the tau2, the imaginary part of the torus modulus, and the energy is like the momentum.
Okay.
So that it is what it is. I don't know what else to say about it. But when I'm actually hitting a horizon, then I have an interpretation for what that quantity is, and that's the entropy. And that just comes from the picture I had at the very beginning. I'll just navigate the slides easier here. So it really comes from here. So it's like saying that basically the trace of e power minus beta h mod is related to the entropy when I can interpret the exponent as a modular Hamiltonian. nowhere else will that necessarily be a modular Hamiltonian, is what I'm trying to say. Well, I mean, you could interpret it. I mean, you could say that I've traced out everything else, but I don't know what that means in the bulk. It's just some funny quantity.
I see. Okay, thank you.
Well, thank you for the question.
Just to follow up on Shiraz's question, what is the is there a particular temperature for the BTC black hole which I should start with, so that when I flow in, then I match onto the de Sitter solution properly in the IR?
No, not necessarily, because well, okay, it depends on how you're doing the matching. If you're doing the matching by just going to some large value of lambda, then not necessarily. If you're doing the matching at the horizon, then yes, and I can't tell you off the top of my head what that should be.
Okay.
So yeah, it's a bit dependent on how you want to do the matching.
Okay.
Vasu, I have a question. It may be a bit vague, but
sure.
Let me still ask. So in that Verlinde Mark Mezai paper, what they showed is that when you put this Dirichlet boundary condition on the cutoff wall, there are the superluminal modes.
Right.
And now you have this eta parameter turned on. Could you tune this eta parameter to get rid of the superluminal modes? I mean, is it even even justified to ask this question?
I don't really know, because eta I'm not really treating as a continuous parameter. I'm really using it as a bookkeeping device, so whether it's 1 or -1, right? Which is ADS or DS. And in both of these cases, the modes will still be superluminal because just because of how things end up working out. Of course, you can change the sign of lambda or mu, then they'll be subluminal, right? Like if you change the sign of mu, but eta, I don't actually know what it means to tune eta.
Right. Right.
Yeah.
Sorry, one more slightly big question. You explained to us that this flow equation that you had was the same as the Einstein constraint equation.
Yeah.
Right, the H00, the time constraint kind of equation. Now, is there some statement about the complete set of solutions of this equation? Are all solutions to this equation basically slicing known finite temperature ADSs and flowing?
That's a good question. So the limitation here is that at least when looking at the torus partition function on the boundary, what I have direct access to is the constant mean curvature sliced. Like I have the constraint equation in a particular gauge, and it's hard to say from there whether you have a complete set of solutions or not. I mean, some would argue yes, others would say no. I mean, there's some classes, at least in higher dimensions, I know that there are classes of spacetimes that cannot be CMC sliced entirely. So I don't really know. Yeah.
Okay, but the equation that you wrote down, all its solutions are mapped to flows in known geometries?
Yeah.
I see. Okay, thank you.
Thank you.
Okay. If there are no further questions, let's thank Vasu again for a very nice talk.
Thank you all.
Thank you, Vasu.
Thank you. It was nice meeting you all.
Yes.
Thank you so much.
Good to see you again, Onkar.